is we are going to calculate what is our torque, or sorry, what is our normal forces, our axial forces, what is our shear force, and also what is our bending moment. Okay, so now I would like to focus on our shear force first, because we are going to have a test on shear force. Okay, so we are going to look at what are the shear forces. Okay, so we're going to do combined loading. As I taught you guys before, combined loading, you have to look at the loading about different planes. Okay, so let's draw our configuration. We know that this is our X, this is our Y, and this is our Z. Okay, so the first thing we're going to look at is we are going to look at the plane, exact plane. Okay, we're going to look at the exact plane. So this is our X, and this is our Z, and right hand rule, this is the rotation of our Y. Okay, so we are going to draw our member. Okay, so this is just a sketch, as you can see, right? And then we have a dotted line. There's the web. And then we put in our elements. Okay, so we know that we have our element A, and we also somewhere around here, that is our element B, right? Then our centroid relative to the element. Okay, I did teach this before in the beginning or after term test 1, right? So this is our centroid. We put in our forces. So we have 2 times by 8 kilonewton. Right? We have a load coming down at 100 kilonewton. And then we have a load in this direction going at 25 kilonewton. Okay, so let's look at the forces first. Okay, so we only need to bother about the arrows, right? We are going to ignore the dots and crosses. Okay, so we can ignore the 25 for now, right? Just for now. So what we have is we have Vx. Okay, we have Vx. Which is equal to 2 times by 8, or which is equal to 2 times 8. Oh, I should not write this. It's basically twice of 8 times 10 to the power 3 is equal to 16 times 10 to the power 3 Newton. Okay. And then if you look at the 2 kilonewton is also generating a force, a moment, right? So moment about Y. Okay, so we know that it's going to generate a moment about Y, and it's going to go into this direction. Right, so this is moment about Y. It's going to be a compression, and this will be in tensile. Right, but before we go on, if we were to look at Vx, right, if we look at Vx, okay, we are going to look at the I-beam now. So this is how the I-beam look like. Right, And all this, we are going to use thin wall analysis. And this is point A, element A. This is element B, right? So we know that the shear force, right? Now you have to remember what you have learned is going this way, is going this way, and then is doing this. So over here, you have your terminal 1, terminal 2, terminal 3, terminal 4, and terminal 5. Okay, so your shear flow is in that direction, and we can see that we are going to apply, right, the formula. So in your mind, you have to more or less know what formula to apply, right? This is X and this is Y. So what we are calculating is the at element A, okay, at element A. So at element A, right, what we are calculating is the shear stress. The intersecting plane is in the Z direction, and the shear is flowing in the X direction, right? The shear flow is in the X direction. So this will be equal to Vx, right? So we know that this is our Vx. So we know that it's going to use Vx over Iyy, right? Qy over T. So what we know is the shear, right? What we know that shear at point A is not equal to 0. However, if we look at point B, it's exactly at the center. The shear at point B is equal to 0. This is where the analysis starts. Okay, there's a lot of formula or there's not a lot of theory that we have to assemble all together now, right? Because at point B is where is our terminal, okay, by using thin wall analysis. And we know at the shear stress at point A is known as our what? White flange. Okay, so i.e. we're going to use Q. Okay, so this is due to what? Shear force in the X direction. Okay, and you have to sketch all this. You have to sketch the what? You have to sketch the Q, the direction of the Q. Okay, this is where it was important. So that is for Vx. So the next thing we know, right? There is a moment about Y, and we are going to assume that it's going anti-clockwise is positive. So moment about Y will be equal to, so if you look at the twice of 8 kilonewton, it's perpendicular to the what? Centroid. So the distance taken has to be the distance from where? From the applied force to the element, which is equal to 0.6 meters. Okay. So moment about Y will be equal to twice 8 times 10 to the power 3 multiplied by the distance, and the distance is going up to 0.6. Is 0.6. So this will be equal to 2 times by 8 power 3 times by 0.6. So the moment is 9,600, right? And this is in Newton meter, right? And you know the formula we're going to apply is normal stress about X is equal to my over Iyy multiplied by a distance X, all right? Moment about Y. Okay, so wait, is it, yeah, distance X. So moment about Y. So we know that this is our moment about Y. So if we look at over here, right, element A, now we start doing the analysis also. So element A will be in what? Will be in compression, right? Because it's over here. It's on the left side, and left side is compression. So you will be in compression. And element B is on the right hand side of the centroid. It will be in tensile. Okay. So any more forces to consider? Yes, we have our P in the Z direction that is equal to 100 times 10 to the power 3 Newton, right? And this 100 times 10 to the power 3 Newton is sorry, this is normal stress about the Z direction. So stress in the Z direction is equal to PZ divided by A, right? And then on element A and also for element B, is going to be in what? Compression, because the 100 kilonewton is coming down. So what we have just done is we have identified that we have a shearing force, okay? We have identified there's a bending moment in the y-axis, and we also have identified that there's a normal stress, right, about the z-axis, okay? So the next thing, so any more to look at? Nothing else. So we look at the next point of view is on the YZ plane. Okay, so next we are going to focus on the YZ plane. Let me get this figure. So next we are going to, I'm going to sketch.
I'm sorry, Eugene. What does the PZ represent?
Axial load about the Z direction.
Mm-hmm.
Okay, so this is basically coming down. This is our PZ.
Why wasn't it like VY? Is it because it's on the centroid?
No, it's at the centroid. It's not. It will not generate
okay.
a shear force. It will generate a normal force.
Okay.
Okay. So the next thing that we are going to look at, okay, we are going to look at a different plane. So the plane that we're going to look at now, okay, so we know that this is our X, this is our Y, and this is our Z. So the next one we are going to look at is we are going to look at the YZ plane. Okay, and then we know that this is rotation about X. Okay, so I'm going to sketch this. Right, so you have, so the view is something like that. You have built in on one side, put in our elements. Okay, so this is our element A. Over here, this is our element B. Okay, and then we put our geometric or our centroid relative to the element of interest. It's directly over here, right? Then we put in our forces. Okay, so we know that we have we know that we have our 100 times 10 to the power 3, right? And then wait, let me see, did I draw this correctly? Yeah. Then we have our 8 times 10 to the power 3, 8 times 10 to the power 3, which we can ignore. And then we have a force coming down here. That's 25 times 10 to the power 3. So let's do the moment first, right? So the moment is going to be about x-axis. Okay, so I'm going to call that this is my moment of x. This is compression. Over this side is tensor. Okay, so we don't need to do px.
I'm sorry, Eugene. I have a question.
Yes.
In the first diagram, the arrow went the opposite way. Like, why is it going this way now?
I'm just making an assumption.
Oh, okay.
You can flip it the other way, it's fine. But if later on when you calculate the value is negative, then you have to change the direction. Okay. So for now, right, we are going to calculate. So I've assumed that clockwise is positive. We're going to calculate moment about x will be equal to now. So this is where students get confused. I think I highlighted before. If let's look at the 100 times 10 to the power 3, right? It's parallel to the what? The 100 is parallel to the geometric centroid. So the distance is basically taken from the centroid to the edge, which is this distance over here, which I'm going to call our y distance. Okay. The 25 you take up to the what? Up to the element. Okay. So let's do up to the element first. Okay. So the 25 times 10 to the power 3. The element is the element is 0.5. Right. The other one, we need some information regarding W200 X 41.7. So I'm going to take this information over here. Bear with me. I'm going to copy. I'm going to come here. I'm going to paste. Okay. And then I'm going to make it small. Right. So we need to know that distance y. Okay. So if we look at the distance y is basically d divided by 2. Okay, it's basically d divided by 2. So the material we're going to use, or the structure we're going to use, is this one. I'm going to highlight is 41.7. Okay. So we know d is what? 205, right? D divided by 2, so 205. So the moment will be equal to plus the direction is the same. 100 times 10 to the power 3 multiplied by d, the value for this 205 in millimeters. In meters is 0.205 divided by 2.